The next product that we want to talk about in terms of vector multiplication, right? We've seen the scalar multiplication um, that vectors enjoy, meaning you can scale vectors by a constant. And now we've seen the dot product, where you take a vector dot another vector and it spits out a number. And we learned some of the meanings and applications of what this number, the dot product, is telling us. There's another kind of product that we can introduce, a product of two vectors. And now the resultant will be the result will be a vector. And let's see why we why we even want to consider this cross product. And let's kind of see where this cross product comes from, or where it can arise naturally. So let's start with an objective here. The objective, given two vectors, let's say u and v, what if we want to find w, some third vector w, such that w is orthogonal to both u and v, to both u and v. Excuse my washer back there. Okay. So here's our goal, or here's the objective, right? Let's say we have two vectors here, u and v. Okay, and what we want to do is be able to find some third vector w such that u and v and w are orthogonal, meaning the angle between v and w is a right angle, but also the angle between u and w is a right angle. Okay, and so we have these three vectors set up in this way. And the question is, like, how can we, what's like an expression or a representation of this vector w just given information about u and v? And the answer is a spoiler. Well, the answer is cross product. So the cross product gets us what we want. Okay, so we'll say, well, let's derive it. Let's derive this formula for the cross product here, an expression for w. So what does it mean for two vectors to be orthogonal? If you'll recall, after we introduced the dot product, we learned the following theorem. So recall, two vectors, let's say like a and b, are orthogonal if and only if their dot products, or their dot product, is equivalent to 0. And so we can use this to our advantage, right? We want something that's perpendicular to two vectors. So when we're using the notation of u, v, and w, let's introduce some more notation here. In component form, u will be u1, u2, u3. V will be v1, v2, v3. And then w will be w1, w2, w3. Okay, and so when we want u and w to be orthogonal, and we also want v and w to be orthogonal, well, u and w orthogonal if and only if u dot w is equal to 0. And v and w orthogonal if and only if v dot W is equal to 0, right? And so now we have like a system of equations here. And unpacking the definition of dot product, we can start to have a system of equations with unknowns. Because what are we trying to solve for? Let's keep in mind what we're trying to solve for. We're looking for this vector v. We're trying to express this vector v in terms of the vectors u and w. And what that means is we are trying to find, so kind of the main goal is w1 equals what? w2 equals what? w3 equals what? Right? Because if we can figure out what w1, w2, and w3 should be, well, we know explicitly what the vector w needs to be, and that's our goal, right? So we need to unpack the definitions of the dot product here, u dot w and v dot w, and see if we can solve for w1, w2, and w3. So let's do that. U dot w is the same thing as u1 w1 plus u2 w2 plus u3 w3, and we want that set equal to 0. Well, also, v dot w is equal to v1 w1 plus v2 w2 plus v3 w3, which is also equal to 0. And again, the goal here now is with these two equations, we want to solve for w1, w2, and w3. Okay, so we can do a little bit of linear algebra here, and like substitution and stuff like that, to our elimination techniques to simplify the expressions. So let's eliminate the variable w3. Right? So if we can eliminate the variable 3 by multiplying the top equation by v3 and the bottom equation by u3 and taking their difference, right? Because then that would give us a term that looks like u3 w3 v3 minus u3 w3 v3. Those would cancel, and we would then just have an expression in terms of w1 and w2. So let's do that. We're going to take v3 times the top, u1 w1 plus u2 w2 plus u3 w3, and then we're going to subtract, whoops, maybe I'll write it one line lower here. We're going to subtract multiplying the bottom equation by u3. Again, we're doing this because I want to eliminate the variable w3. So this will be v1 w1 plus v2 w2 plus v3 w3. And if we eliminate this here, you can see we get the following thing. We get v3 u1 w1 plus v3 u2 w2 plus v3 u3 w3 minus u3 v1 w1 minus u3 v2 w2 minus u3 v3 w3. And all of this was just an algebra trick to cancel these terms here. And now, remember, this should be equal to 0 still, right? This whole thing is equal to 0 because we took, on the left, we took like v3 times the top minus u3 times the bottom. But if we did that to the right-hand side of the equation, we'd have 0 minus 0, which is still 0, right? So this entire expression should be equal to 0. And now we can regroup these slightly differently. We can regroup what's left by combining the terms. We can factor out a w1 of what I've enclosed in green, and we can factor out a w2 of what I've enclosed in blue. And that should include the negative there, right? So I don't want to forget that minus sign. And so let's do that and see what we get. If we pull out a W1 from the two terms enclosed in green, it looks like we'll have V3U1 times or minus U3V1. So we're going to get U1 V3 minus V1 U3 times W1, right? Yes. Okay, and then we can do the same thing for W2 here. It looks like we'll then have plus, and in this term we're going to have V3, so U2 V3 minus V2 U3 times W2, and this should be equal to 0. And so now we want this equation to be equal to 0. How can we get this equation to be equal to 0? Well, then we would want that U1 V3 minus V1 U3 times W1 is equal to negative U2 V3 minus V2 U3 times W2. And so maybe you can see from here, for this equation to be satisfied, we can choose W1 and W2, right? We can choose W1 to then be U2 V3 minus V2 U3, and we can choose W2 to be negative U1 V3 minus V1 U3. We just kind of see, like, we say, okay, well, we have this term over here, and if we want cancellation in this formula, we can just set W2 equal to be negative of whatever was over here, and this gives us the cancellation we want. And then the negative with the negative out front makes a positive, so then to make this equation true, we just had to set W1 equal to whatever was on the other side of this equation. And so you can plug these in to verify that these are valid solutions for this equation. So we have W1 equals U2 V3 minus V2 U3, and then W2 is negative, quantity negative, U1 V3 minus V1 U3. Okay, and now, so we've answered our questions about W1 and W2, but what about W3? Well, you can do a bit more algebra here. I'll save us the tedious algebra. You know, what you would do is come back to the original equations up here. You would plug in what we learned for W1 and W2, and then you would solve for W3. Or, you know, you would just have to plug in one. You wouldn't even have to plug in both. Like, just pick like the top equation, say, and then plug in W1, plug in W2, solve for W3. If you do that, so plug in, simplify, get W3. Okay, so this is kind of the steps you would take to get W3. And if you do so, you get U1 V2 minus U2 V1. And so here, through this tedious linear algebra, or through this tedious algebra of solving a system of equations with a handful of unknowns, we've now expressed the vector W in terms completely of the vectors U and the vectors V, or the vectors U and V. So let's kind of write this concisely now. What we've learned is that if U is U1, U2, and U3, and V is V1, V2, V3, then W that's orthogonal to both of them, right? Then W orthogonal to both can be represented as follows. The first component was U2V3 minus V2U3. And then in the second component, it was negative U1V3 minus V1U3. And then in the third component, we have U1V2 minus U2V1. Angle brackets here. That's the end of the vector. And so this is our vector. If we have a vector U and a vector V, U and V, and we want something orthogonal to both of them, this is the formula. So like here's a right angle and here's a right angle there, right? And so this is the formula that gets us a vector that's perpendicular to U and to V. Now, this is what we call the cross product. We say, so here's a definition. We say W, given by this long formula above, is the cross product of U with V. And we say W is equal to U cross V. We write this as a cross product here. So notice, like for the dot product, we represent the dot, or we use the dot symbol, right? And for a cross product, we use a cross or an X. And so when you want to compute the cross product of two vectors, you have to look at their components and plug them into this big old formula here. And so that can be a little tedious. And we'll see later there's actually a much nicer way of calculating cross product that doesn't involve memorizing this formula. If you stare at it long enough, you can start to see patterns. You know, it's like U2, V3, and then the indices flip. So V2, U3, and then the second component is negative, and then it's U1, V3, and then the indices flip again. So it's minus V1, U3, right? And so you can see there's some pattern to this, and you could memorize it. But what we'll see in a little bit is that using matrices and determinants, there's a really nice way to calculate the cross product that bypasses any sort of memorization task. Let's, as always, once we learn a new definition or a new operation or whatever, we want to put this to use so we can see, how do we actually use this? What do we learn from this? So let's let P be the vector -1, 2, 5, and Q be the vector 4, 0, 3. Now let's find the cross product P cross Q. Okay, and so down at the bottom here, I'm going to remind myself what U cross V is, right? It's U2 V3 minus U3 V2, and then it's negative U1 V3 minus U3 V1. And then it's going to be in the last component, we have U1 V2 minus U2 V1, right? And so there's our formula for the cross product. And the reason why is because, you know, if you'd like to just stare at this formula, have it kind of juxtaposed to the problem you're solving. And you can just kind of say like, okay, well, this is U1, this is U2, this is U3, and then this is V1, this is V2, and this is V3. And then you can just kind of plug in, right? So what's P cross Q? Well, it's going to be U2 V3. So it's going to be 2 times 3 minus U3 V2. So U3 is 5 and V2 is 0. Okay, that's the first component. The second component is negative U1 V3. So that's negative 1 times 3 minus U3 V1. U3 is 5, V1 is 4, comma. And then the third component is U1 V2. And so that's negative 1 times 0 minus U2 V1. So U2 is 2, V1 is 4. Okay, and so now we can just kind of simplify the arithmetic that we have lined out for us. So in the first component, we have 6 minus 0, which is 6. In the second component, it looks like we're going to have negative 3 minus 20. So negative 3 minus 20 is negative 23, but it's minus a negative 23. So that's actually a positive 23. Right? Again, just simplifying the arithmetic in the second term there, or in the second component. And then again, it looks like we have 0 minus 2 times 4. So the third component is negative 8. And so the cross product P cross Q is 623, negative 8. Okay? And so that's how you, at this step, that's how we're going to compute the cross product, is just stare at the formula, figure out what components are labeled by what UI or VI or whatever, and then simplify. And so for the sake of practice, let's say this said find P cross Q and Q cross P. Let's do Q cross P here. I want to see if we get the same thing. If we do Q cross P, then we flip what we call U and what we call V. So now for P cross Q, we were abiding by my red subscripts here. Now let's abide by the blue one. So now P is V1, V2, V3, and Q is U1, U2, U3. And so if we do this, then let's see what we get. We get U2, V3. So that's going to be, U2 is 0 in this case, so it's going to be 0 minus U3, V2. And so that's minus 2 times 3. In the second term, we have negative, parenthesis, then we have U1, V3. So that's 4 times 5, so that's 20. And then minus U3, V1, which is minus a negative 3, so that's plus 3. Okay, and then in the third component, we have U1, V2, which is, looks like it's going to be 4 times 2, which is 8, and then minus U2, V1. But U2 is 0, so that's 0. And so Q cross P is negative 6, negative 23, 8. And you may notice that these are different, and that's expected. And actually, you can see that they're the negative of each other. So what we just calculated is that P cross Q is equal to negative Q cross P. And this is not an anomaly. This happens all the time because the cross product has an anti-commutative property. Not the commutative property, but the anti-commutative property, meaning if you switch the order, you must pick up a negative sign. So here was a first example, a kind of sneak peek into showing that the cross product is anti-commutative. And so I wanted to use that as a quick example. The next thing I want to say, there's a handful of there's a remark and some properties I'd like to go over for now. So let's take a look at what we have. There's quickly a remark, and this is about the geometry of the cross product. Okay. The direction, so given vectors u and v, the direction of the cross product is determined by the right-hand rule. And you'll remember in my a few videos ago, I discussed what the right-hand rule was in terms of making sure that your coordinate system in three-dimensional space is correct. And remember, basically what we had was you take the x-axis, so you have the x and the y-axis, and you want to determine which direction does the z-axis belong. Well, you stick your hand in the direction. So I'll draw a hand here. This is the right-hand rule. You stick your hand in the direction of the positive x-axis, and you curl your fingers towards the positive y-axis. So you would, in this picture here, we would curl our fingers this way. And this tells you where your thumb is pointing, you make a thumbs up. Where your thumb is pointing tells you the direction of the positive z-axis. And this is called the right-hand rule because you must do this with your right hand. You take your right hand, you point it in the positive x-axis direction, you curl your fingers towards the positive y-axis, and your thumb determines which way that the z-axis should be facing for a positively oriented coordinate system. Now, when I say that the cross product is determined by the right-hand rule, it's no different. So analogously here, if we have vectors u and v here, and I take my right hand and point it in the direction of the positive, or in the direction of the u vector, notice my hand, to be able to curl my fingers towards v, I have to have my hand facing down, right? I would be giving a thumbs down here. And I curl my fingers towards v with my right hand, and my thumb is pointing down, which tells me in this picture, tells me that the cross product is pointing down. Here is u cross v, down here. However, if I were to look at a picture where u and v were situated differently, right? Say something like u here and v here. Now if I took my hand in the direction of u to curl my fingers towards v, my hand would be oriented like this. And when I curl my fingers in the direction of v, I get a thumbs up instead of a thumbs down, which tells me in this picture, u cross v is facing up. And so one thing we can kind of start to put together geometrically here is, like I said, that, and we'll get to, I'll state the property formally in a second, but that the cross product is anti-commutative. And if the cross product is anti-commutative, geometrically, that means that we just flip the direction. So in this picture over here, this, the red arrow, is v cross w. And over here, the red arrow, v cross w, would be facing up. And so you can see kind of a geometric interpretation of the cross product now, and how the direction of our cross product is determined by the right-hand rule. Okay, and so that was an important remark I wanted to make. Next, I would like to just state some handy results and a handful of properties. So first, let's compute the cross product of standard unit vectors. This will be very important as we move forward. Okay, so remember our standard unit vectors are I, which is 1, 0, 0, j hat, so I hat, which is 1, 0, 0, j hat, which is 0, 1, 0, and k hat, which is 0, 0, 1. Okay, these are our standard unit vectors, right? And now let's just take a handful of combinations. We could take I cross j, and let's think about this geometrically here, without even plugging into the formula for cross product. Let's think about this geometrically. If we have three-dimensional space here, say x, y, and z, and we're looking at I hat cross j hat, and we want their cross product, right? Well, the cross product, the direction is determined by the right hand rule. And so if we took our hand in the direction of I hat, which corresponds to the positive x-axis, and curl our fingers towards the positive y-axis, which corresponds to the direction of j hat, you can see we would be taking our hand like this and curling our fingers this way. And that would give us a thumbs up, which means whatever I cross j is a unit vector that's perpendicular to both the x and y axis. So that means it lies along the z axis. And so this here is I hat cross j hat. And geometrically, you can interpret, you can kind of interpolate that this is just k hat. So I hat cross j hat is k hat. And maybe I'll leave it to you guys to just verify this with the formula. Plug in, like for I hat cross j hat, you know, just take this to be u and this to be v, and then plug in the formula and see what you get. And you should get the vector k hat. You can do something similar with j hat cross k hat. If you take j hat cross k hat, that means you're going to put your hand along the direction of the positive y-axis, so, and curl your fingers towards the z-axis. So in that case, your hand would have to be flat, and you would have to curl your fingers up towards the positive z-axis. And your thumb is pointing in the positive x direction, and it's a unit vector, so we get that j hat cross k hat is I hat. And by a similar argument, you can see that k hat cross I hat is j hat. So here's a list of cross products of standard unit vectors. And knowing that the cross product enjoys the anti-commutative property means that we can flip the order here and say that j hat cross I hat is negative k hat cross j hat is negative I hat, and I hat cross k hat is negative j hat. A lot of hats here today. So I would definitely record these and keep them in mind. As we're going through computation, it can save your life, or it can make your life a lot easier when going through tedious computations here. And so next, let's just look at, let's observe a list of properties here. Properties of the cross product. The first one we've already discussed and seen a particular situation of when this holds, and it's that the cross product is anti-commutative. Anti-commutativity means that once you flip the order in which you perform the operation, you have to pick up a negative. So U cross V is negative V cross U. We have that the cross product is distributive over vector addition. So it is distributive, meaning if we took U cross V plus W, this is the same as, here, maybe I'll write this down one line so I can fit it all. We have U cross V plus W is the same as U cross V plus U cross W. You see here we can distribute the U to both the V and the W when taking the cross product. And one reason this may be helpful is actually to go in the opposite direction. It would be to start on the right-hand side of this equation and go backwards. Because if you notice over here, you would have to compute two cross products. However, we know if the cross product is distributive, over here, you can just take vector addition and then only have to take one cross product. So we could have an advantage there. The third property I'd like to discuss is multiplication by a constant. Multiplication by a constant. Okay. Similar to the associative property of the dot product here, it's if you take, let's let K be a real number. K, so we're scaling the vector U cross V by K here. This is the same as first scaling U by K cross V, which is also the same as first scaling V by K and then taking U cross KV. So this is another property we have. The fourth property is that is dealing with the zero vector. And basically it says that the zero vector acts as you would expect. And it says that V cross the zero vector is the same as the zero vector cross V, which is 0. And you could prove this pretty quickly just by looking at the formula for cross product and seeing that, okay, every term then would have a 0 in it. So the whole vector vanishes. Next property I'd like to discuss is the cross product of a vector with itself. Cross product with itself. And I'd like you guys to kind of go through and see if you can prove some of these, just as I asked if you could prove the dot product ones. That if you take a vector and cross it with itself, you get 0, right? And this makes sense geometrically, because how could you get a vector that's perpendicular to V and itself, right? And so you get the 0 vector. The last property I'd like to talk about is a semi-definition, but also a property here, and it's called the scalar triple product. I'll introduce the scalar triple product a lot more rigorously in the next video. But for now, we can just talk about what it is. And the scalar triple product is U dot V cross W. This is the scalar triple product. And the property here is that this is the same as U cross V dot W. So here's a handful of properties that that the cross product enjoys. Now, I'd like to do a quick example. And then I think I would like to do a quick example. I would like to state a theorem, and then in the next video, we can talk about determinants and using determinants to calculate the cross product a little more smoothly. So let's compute in this example. Let's compute 2i hat cross 3j hat, the whole thing cross j hat. Okay, and so we have 2i hat cross 3j hat cross j hat, and we want to see what this equals, right? And when you see some sort of expression like this, you know, you don't want to just plug this in and grind your way through it. If you have to, you have to, but one way out of this is using these properties and remembering the cross product of standard unit vectors here. So you can see, first, I want to simplify our expression by using property 3 here, which says I can pull a constant anywhere I want in the expression and it's still equal. So because of that, I can pull the 2 out of this expression, and this expression becomes 2i hat cross 3j hat cross j hat. And I can do the same thing again with the 3. This makes the expression 6i hat cross j hat cross j hat, right? I use property 3 twice here, or like this kind of associativity with a scalar property. And now I know what I hat cross j hat is, thanks to the computations I've done beforehand here. I know I hat cross j hat is k hat. And so this expression becomes 6 times k hat cross j hat, right? But it's kind of, the parentheses would be here, if you will. And now, so let's kind of record where I'm at here. So I have 2 I hat cross 3 j hat cross j hat is actually, where we've simplified it to so far, is 6k hat cross j hat. I can use this third property again and put the scalar anywhere I'd like. And so I can say, well, this is the same then by property 3 is 6 times k hat cross j hat. And I think back to what k hat cross j hat was, and it's negative I hat. Right? We can come back here and verify. I have k hat cross j hat is indeed negative I hat. And so this entire expression simplifies to negative 6 I hat, which is the vector negative 6, 0, 0. So there's an example of understanding the cross product and being able to use some of its basic properties. Now, the last thing I would like to discuss is a quick theorem, because we have not yet discussed magnitude of cross product. We've just discussed the vector itself. And quickly here, a theorem would be that if we have two vectors, u and v, and some angle between them theta, right? And we can calculate the cross product. You know, this would be like u cross v up here, this perpendicular vector, or this orthogonal vector. The theorem is that the magnitude of u cross v is the magnitude of u times the magnitude of v times sine theta, okay? And so this is one way that we can calculate the magnitude. Of course, u cross v is still some vector, right? So it has components, which means you can also compute the magnitude just by the standard, take the square root of the sum of the components squared. But this theorem will be pretty important as we use the cross product in the future, and especially in physics applications that we'll see in the next video. And so this was all I wanted to say about cross products so far. We learned the definition, how to compute them, some basic properties, and now a statement on the magnitude. And in the next video, I'd like to look at using determinants to make our lives easier when computing the cross product. I'd like to talk about the triple scalar product a little more in depth because it has some nice applications. And then I'd quickly like to introduce where the cross product arises in a physical setting. So, and we'll get to all that in the next video.